Hello. Today I want to discuss about robot inverse kinematics and how you can perform robot inverse kinematics using an optimization. So let us look at first at what do I mean by robot inverse kinematics. So I want to discuss about inverse kinematics using optimization based methods. Let us take an example of a simple robot, a planar 2-hour robot, which looks like this. This is a planar 2-hour robot. Here, R means that there are two revolute joints. We have to perform the inverse kinematics of this robot. What does that mean? So this robot has two revolute joints. The first one makes an angle, moves the link, the first link by an angle θ1. The second revolute joint moves the second link with the angle θ2. So this is link 1 that has length L1. This is link 2 that has length L2. And based on the angles θ1 and θ2, the tip of the robot will reach some position xt, yt. Our goal here is to find θ1 and θ2 for any given xt and yt. It turns out that this problem of inverse kinematics to find θ1 and θ2 for a given xt and yt is a difficult problem. However, another problem called the forward kinematics, in which we find xt and yt given θ1 and θ2. That is a relatively simple problem. And I can write the expressions here of xt as L1 cos θ1 plus L2 cos θ1 plus θ2. So here it is easy to see that if I extend this line and if I draw these perpendiculars, so this length is L1 cos θ1 and this length is L1 cos θ1 plus θ2, because the line L2 makes an angle θ1 plus θ2 with the x-axis. Let us also show the x and y axis here. Given these x and y axis, the angles θ1 and θ2, xt, the tip position, can be written like this. Also, I can write the y component of the tip position, that will be written as L1 sine theta 1 plus L2 sine theta 1 plus theta 2. All we have to do to get the tip position is to plug in the values of theta 1 and theta 2, and we get the tip position. Plug in the values of to get the tip position. We have to plug in the values of theta 1 and theta 2 to get the tip positions. However, so this is the forward kinematics problem. This forward kinematics is easy. The other problem, which is the inverse kinematics problem, is difficult. In the inverse kinematics problem, I would supply to you the values of xt and yt, and you have to find the values of theta 1 and theta 2. We can take an example here because examples will simplify and clarify your understanding. Let us say that L1 is equal to 1 centimeters, L2 is equal to 1 centimeters. We are trying to perform the forward kinematics for a particular value of theta 1, say pi by 3, and a particular value of theta 2, say pi by 6. Yes. So x tip will be given by L1, which is 1, cos theta 1, which is pi by 3, plus L2, which is again 1, cos theta 1 plus theta 2, which is pi by 3, plus pi by 6. This will evaluate to, let's see, so pi by 3 is 60 degrees and pi by 6 is 30 degrees. So what we have is 1 into cos 60 degree. Cos 60 degree is 1 by 2, and plus 1 plus cos 90. Cos 90 is actually 0, right? Cos 90 is 0. So this whole thing becomes 1 by 3. Similarly, y tip will be given by 1 sine pi by 3 plus 1 sine pi by 3 plus pi by 6. So this value will be 1 into root 3 by 2 plus 1 into sine of 90 degree, which is 1. Okay. So root 3 by 2 plus 1 is the value that we will get here. I will just quickly check whether these values are correct or not. So I will use a calculator to compute these values. I can also use maybe use MATLAB, compute these values. So we have cos pi by 3 plus sine pi plus cos pi by 3 plus pi by 6. There is 0.5, and then I can also check about second expression, which is also correct because under it 3 divided by 2 plus 1 is 1.8660. Okay. So these are the values. This is equal to 1.8660. This is equal to 0.50. Now we have the value of X tip and Y tip. We have the value of X tip and Y tip. Now let me pose the inverse problem. Given that L1 is equal to 1 meter, L2 is equal to 1 meter, these lengths are the design of the robots, so they do not change for different inverse and forward kinematics problem you want to solve. L1, L2 are given. Let us say X tip comma Y tip is equal to 0.5000 and 1.8660. Given that X tip and Y tip are these, can you find the value of the angles theta1 and theta2? One way of solving it is to go back to these equations. These are trigonometric equations, and these trigonometric equations can be solved analytically by doing some algebraic manipulations like squaring X up, adding them, subtracting something. So these are two equations and two unknowns, right? So these should be solvable. But this whole activity is a little cumbersome, and sometimes for general robots, this kind of a solution may not be possible. Therefore, we want to pose this problem as an optimization problem. We want to pose the inverse kinematics problem as an optimization problem. When you want to pose the inverse kinematics problem as an optimization problem, we have to find an objective function which, when minimized, would give us the angles which reach a certain target. Suppose xd comma yd is the desired tip position. If I define an objective function, which is a function of theta1 and theta2, as xd minus x tip. So x tip is a function of theta1 and theta2, which is this function. Y tip is also a function of theta1 and theta2, which is this function. If I define the objective function like this, if I define the objective function like this has a special property. this objective function is sum of two squared terms. This objective function is the sum of two squared terms. That's the first thing. The minimum value, this also implies that the minimum value of this objective function is 0. And when does this objective function acquire or obtain the 0 value? 0 value is achieved when both the terms are 0. So the 0 value will be achieved only when the term 1 here is equal to 0, and the term 2 here is also equal to 0. If it is anything but 0, suppose it's some positive value or some negative value, the sum, that positive value squared or that negative value squared and sum together will not be equal to 0, right? So the objective function has the minimum value of 0, and this 0 value of the objective function is achieved only when both the terms that we have defined in the objective functions become 0. Both these terms becoming 0, this implies that we have found the values of theta 1 and theta 2 that will make the target, the tip position, equal to the desired tip position. Similarly, the y coordinate of the tip position equal to the desired tip position. So those values of theta 1 and theta 2 that make the actual value of the tip position equal to the desired value of the tip position, that is the outcome of this optimization process. Both xt and yt achieve their desired values. Right? Now, this is a pretty straightforward problem. What do we have here is a nonlinear optimization function. We have a nonlinear optimization function here. So this optimization function, so we have a nonlinear, let us call this not the optimization function, but the objective function. So we have a nonlinear objective function in two variables. We have a nonlinear objective function in two variables, right? Since we have a nonlinear objective function in two variables, this can be solved, this problem can be solved with any kind of multivariable optimization algorithms, for example, Cauchy's steepest descent algorithm. So this can be solved using the Cauchy's steepest descent algorithm. So that is all I wanted to discuss about formulating the objective function for performing inverse kinematics of a 2-hour robot. And this is general in principle, so you can do it for any robot. Another thing that we can mention is about the range for the two angles, which will be, let us say, from minus pi to pi. So these are the variable bounds, and that is the objective function. So these are variable bounds, and that is the objective function. So this is uh, what I mean by formulating the problem as an optimization problem.